A sulfonic acid refers to a member of the class of organosulfur compounds with the general formula Rs equals O, to a euro OH, where R is an organic alkyl or aryl group and the S equals O, to a euro OH group a sulfonyl hydroxide. A sulfonic acid can be thought of as sulfuric acid with one hydroxyl group replaced by an organic substituent. The parent compound is the hypothetical compound sulfurous acid. Salts or esters of sulfonic acids are called sulfonates. Preparation. Sulfonic acid is produced by the process of sulfonation. Usually the sulfonating agent is sulfur trioxide. A particularly large-scale application of this method is the production of alkyl benzene sulfonic acids, Rc6H5 plus SO3 Rc6H4SO3H. In this reaction, sulfur trioxide is an electrophile and the arene undergoes electrophilic aromatic substitution. THIOLS can be oxidized to sulfonic acids, RSH plus 3 harbs-O2 RSO3H. Certain sulfonic acids, such as perfluorooctane sulfonic acid, are prepared by electrophilic fluorination of preformed sulfonic acids. The net conversion can be represented simplistically: C8H17SO3H plus 17F2 or C8F17SO3H plus 17HF. Properties: sulfonic acids are much stronger acids than the corresponding carboxylic acids. P-toluenesulfonic acid, with a pKa of -2.8, is about 1,000,000 times stronger acid than benzoic acid, with a pKa of 4.2. Similarly, methanosulfonic acid, pKa equals -1.9, is also about 1,000,000 times stronger acid than acetic acid. Because of their polarity, sulfonic acids tend to be crystalline solids. They are also usually colorless and non-oxidizing, which is convenient. Because of their high acidity, sulfonic acids are often soluble in water or exhibit detergent-like properties. The structure of sulfonic acids is illustrated by the prototype, methanosulfonic acid. The sulfonic acid group, RSO2OH, features a tetrahedral sulfur center, meaning that sulfur is at the center of 4 atoms, 3 oxygens and 1 carbon. The overall geometry of the sulfur center is reminiscent of the shape of sulfuric acid. Representative sulfonic acids and derivatives. Applications: although both alkyl and aryl sulfonic acids are known, most of the applications are associated with the aromatic derivatives. Detergents and surfactants. Detergents and surfactants are molecules that combine highly nonpolar and highly polar groups. Traditionally, soaps are the popular surfactants, being derived from fatty acids. Since the mid-20th century, the usage of sulfonic acids has surpassed soap in advanced societies. For example, an estimated 2 billion kilograms of alkyl benzene sulfonates are produced annually for diverse purposes. Lignin sulfonates, produced by sulfonation of lignin, are components of drilling fluids and additives in certain kinds of concrete. Dyes. Many if not most of the anthraquinone dyes are produced or processed via sulfonation. Sulfonic acids tend to bind tightly to proteins and carbohydrates. Most washable dyes are sulfonic acids for this reason. P-crazidine sulfonic acid is used to make food dyes. Acid catalysts. Being strong acids, sulfonic acids are also used as catalysts. The simplest examples are methanosulfonic acid, CH3SO2OH, and p-toluenesulfonic acid, which are regularly used in organic chemistry as acids that are lipophilic. Polymeric sulfonic acids are also useful. Dowwex resin are sulfonic acid derivatives of polystyrene and is used as catalysts and for ion exchange. Naphthalene, a fluorinated polymeric sulfonic acid, is a component of proton exchange membranes in fuel cells. Drugs. Antibacterial drugs. Sulfur drugs are produced from sulfonic acids. Flow batteries. Methanosulfonic acid is used as the supporting electrolyte of the zinc cerium and lead acid flow batteries. Reactions. Esterification. Sulfonic acids can be converted to esters. This class of organic compounds has the general formula RSO2OR. Sulfonic esters such as methyl triflate are considered good alkylating agents in organic synthesis. Such sulfonate esters are often prepared by alkoholysis of the sulfonyl chlorides, RSO2Cl plus Rho or SO2OR plus HCl, halogenation. Sulfonyl halide groups occur when a sulfonyl functional group is singly bonded to a halogen atom. They have the general formula RSO2X where X is a halide, almost invariably chloride. They are produced by chlorination of sulfonic acids using thionyl chloride and related reagents. Displacement: although the CSO3 hours bond is strong, the CSO3 bond can be cleaved by certain nucleophiles. Of historic and continuing significance is the I plus or minus sulfonation of anthraquinone followed by displacement of the sulfonate group by other nucleophiles, which cannot be installed directly. An early method for producing phenol involved the base hydrolysis of sodium benzenesulfonate, which can be generated readily from benzene. C6H5SO3 Na plus 2 Na or C6H5OH plus Na 2SO3 plus H2O. Environmental concerns: sulfonic acid derivatives are generally not derived from natural precursors and tend to biodegrade slowly. Some, such as perfluorooctanosulfonic acid, have been detected in the serum of humans. This should be not surprising as all organic fluorine compounds have extreme stability, and low to zero biodegradability. Many are intended to withstand harshest chemical conditions, for example Teflon. The non-fluorinated sulfonic acids tend to have low toxicities. References: A. B. March, J. A. OE Advanced Organic Chemisya 4th ed. J. Wiley & Sons, 1992, New York. ISBN 0-471-60180-2. Coswick, K. A. OE Surfactants and all manner unregistered trademark S. Encyclopedia of Industrial Chemistry 2002, Wiley VCH, Weinheim doi, 10.1002/143567A25 A. B. Hans Samuel Bian, Joseph Stowitz, Klaus Wandliger OE Anthraquinone dyes and intermediates Allman's Encyclopedia of Industrial Chemistry 2002 Wiley VCH, Weinheim doi, 10.1002/143567A02355, Guido Busker Acid Catalysts and Industrial Hydrocarbon Chemistry Chem. Rev. 2007, 107, 5366-5410. doi, 10.1021/CR068042E, Manfred Weber, Marcus Weber, Michael Klein-Boyman Phenol in Ullmann's Encyclopedia of Industrial Chemistry 2004, Wiley VCH. doi, 10.1002/143567A19299 Pub 2. Bin Wang, Fukiyu Aino, Gangyu, Junior Huang, Maizatoshi Morita. The pollution status of emerging persistent organic pollutants in China. Environmental Engineering Science 2010, Volume 27, pages 215-225 doi, 10.1089/ES. 2009.0337, Grime H., J. Ahlers, Abias, B. Broecker, H. Hollander, H. P. GELBKE, H. J. Klimisch, I. Mangelsdorf, A. Payetz, N. Paragraph N. G. Strop, R. Vogel, C. Weber, K. Ziegler Skylakakis, E. Biotoxicity and ecotoxicity of sulfonic acids, Structure-Activity Relationship Chemisphere Volume 28, Issue 12, June 1994, pages 2203-2236. doi, 10.1016/0045-6535, 94, 90188-0. Other reading, J. A. Titus, R. Haugland, S. O. Sharrow and D. M. Siegel, Texas Red, a hydrophilic, red-emitting fluorophore for use with fluorescein in dual-parameter flow microfluorometric and fluorescence microscopic studies. J. Immunol. Methods 50, ppA 193 €204 doi, 10.1016/0022-1759, 82, 90225-3 PMID 6806389, C. Lefebvre, H. C. Kang, R. P. Haugland, N. Melexady, S. Arctamankel, and R. P. Haugland, Texas Red X and Hodamine Red X, new derivatives of sulfurhodamine 101 and lysamine B with improved labeling and fluorescence properties, Bioconj Chem 1996, 7, 4, 482-9 doi, 10.1021/BC 96034p.